Good afternoon, and good morning to those joining on the West Coast. Everybody's going to be muted today, and names have been changed for privacy. My name is Jason Smolinski with Polygon Composites. Today, we will be discussing designing composites into minimally invasive surgical devices. Our goal is to educate you on the benefits of composites and to provide you with some resources to help you determine if they are fit for your next project. Before I introduce our speakers, let's briefly touch on the type of composites we will be discussing today. As many of you know, a composite is made of two or more materials with different physical and chemical properties that, when combined, they produce a material with unique characteristics from the individual components. Composites can be produced from a wide variety of materials and processes. For the purpose of this presentation, we're going to be focused on continuous fiber and thermoset resin composites. For those who are not aware, Polygon has been designing and developing advanced composites for over 70 years, serving multiple industries, including the medical field. Today's speakers will be Sam Hart and Jeff Dubach. Sam is Polygon's medical sales manager, serving many of Polygon's medical customers globally. Jeff has been an application engineer in the composite industry for 6 years, focusing on composite applications in the medical field. We will have some time to answer any questions at the end of this presentation, so please feel free to send them at any time. Since we have everybody muted for the duration of this presentation, please direct any questions to Polygon questions in the chat box, and a copy of this presentation will be made available for anyone interested. The minimally invasive surgical instruments market is continuing to grow year over year. The market growth is largely driven by factors such as advantages of minimally invasive surgeries over traditional open surgeries. Sam would like to expand on this a little further.
Sure, thank you, Jason. I'm excited to discuss this topic today. Thanks to the attendees for taking time out of their days to tune in. We hope it's useful for you. I have been with Polygon for over 4 years, and I work closely with many of Polygon's medical customers from concept right through to product launch. Today's market poses unique challenges and opportunities to medical device manufacturers and engineers. We understand regulations globally continue to change. Designers are always looking at ways to be innovative and stand out from the crowd. Surely, one of the most important considerations for any surgical device is the safety of both the patient and the provider. Reducing the potential for error in the operating room is not only critical to the patient's health, but is also essential for protecting the operator and the device manufacturer. Therefore, all materials and components must be consistent, perform as expected, and for the duration of time of use. Next, a significant amount of care needs to be undertaken when considering and maintaining the well-being of the patient while improving outcomes. Whether it's the ability to make smaller incisions, maybe it's causing less trauma or shortening the length of the operation, these are all geared towards reducing recovery times and ultimately improving patient health. Medical device companies are constantly looking for innovative ways to stay ahead and overcome obstacles. They use new but proven technologies to meet the needs of the market. Designers are also challenged to supply devices that are cost-effective without sacrificing quality, functionality, or the integrity of the device. Therefore, components must be performing as expected and consistent. Given that patient safety is of first importance, it is critical that engineers and manufacturers choose proven materials that will meet the supply demand of today's market. Designers want materials that meet their needs and suppliers that are flexible and easy to work with. So how can composites help? The unique challenges we have just spoken of can require new and adaptive technologies to meet the requirements of the industry. Composites provide some valuable benefits to surgical applications, and more specifically, continuous fiber composites contain real advantages and alternatives to current materials in the market. A lot of surgical devices require rigid shafts or cannula to be the connection between the handpiece and the end effector, or to house things like cables or other mechanical components. Unlike molded plastics or extrusions, composites can often be a drop-in replacement for metal or other rigid structures. Composites are not new to the medical world. For over 20 years, they've been successfully used in a variety of surgical applications. Let's consider other industries. Common uses for composites include aircraft, boats, bikes, pneumatic and hydraulic cylinder assemblies, sports equipment, with a reason for success often being the ability to reduce weight as well as being strong. This is beneficial also for medical devices. Composites provide the ability to create unique fiber orientations, allowing tubes and shafts to meet the mechanical requirements of the application. Next, sterilization is an important part of the surgical procedure, so components are needed that can be used with standard techniques such as autoclave, ETO, and gamma. Thermoset composites are compatible with all of these techniques and therefore have the ability to be used in both single and multi-use devices. We understand that designing devices that are utilizing energy or those that might come into contact with electrical energy in the body, an obvious consideration is making sure electricity does not escape. A major cause of laparoscopic electrosurgical injuries is insulation failure. Metal instrument shafts need to have added material or coatings to provide a layer of insulation. So composites, such as glass fiber reinforced, are inherently non-conductive through the entire cross-section, not allowing current to escape even when scratched or nicked. Therefore, it's arguably one of its greatest benefits to devices used in electrosurgical applications. This also allows designers to reduce the bill of materials for the device and also simplifies the supply chain. The ability to work with a material that can be adapted to meet application needs is a benefit. For instance, designers may require a tube or shaft to withstand axial loads or pressures, so fibers can be added in off-axis directions to achieve the desired results. Of course, any medical device needs to be biocompatible, and while validation is necessary through the development process of new devices, it does provide a certain comfort level when the components have already proven to be biocompatible, which can be the case for composites. There may be opportunities to add logos for marketing purposes or requirement to have depth markers, for instance. Composites have multiple coatings and markings available to meet those needs. As you can see, there are many ways composites have the ability to be a solution to the challenges faced when designing minimally invasive devices.
Thank you for that overview, Sam. Before we move on, though, we had some questions sent in before the webinar regarding machine features and what is possible with such composite material. Do you mind touching on that briefly?
Sure, of course. In fact, composites, they can be successfully machined similarly to materials such as stainless. Because it's not a molded plastic, machine features are added as a secondary operation. In Polygon's case, we do this in-house. It's common for us to machine features such as counterbores, grooves, holes and notches, and tolerances can be held tightly.
Okay, we're now going to turn it over to Jeff and to discuss composites, how they're used today, and then what the future may hold.
Thank you, Jason. As Jason mentioned earlier, I've been working with composites in the medical field for going on 6 years now. When looking at composites today, their versatility allows for use in numerous applications. such as prosthetic limbs, orthopedic fixation, and of course, surgical devices. As mentioned before, the focus today is on continuous fiber thermoset composites and how they can be applied in minimally invasive surgical devices. One of the most common ways composites are used in minimally invasive surgeries are as rigid shafts for a variety of procedures. Their lightweight, high-strength properties are ideal for use in devices such as endoscopes, scissors, graspers, and those especially designed to reduce surgeon fatigue. As electro and robotic surgeries have gained in popularity, the need to insulate components and other supporting devices has increased. Non-conductive composites have shown to be a solution to these challenges while still maintaining excellent mechanical properties. These mechanical properties can also be enhanced by factoring in multi-lumen designs into the final product. For instance, the device designer may wish to incorporate multiple conductive paths or insert components such as cables or light sources within the shaft, which is possible using composites. A more recent example would be interventional oncology, where the focus for more isolated and precise treatment of tumors require the need for insulated shaft introducers. To some extent, the full benefit of using composites in medical devices is yet to be fully realized in today's market. As you can see on the slide in front of you, these are just a few of the ways that composites are used today, but the possibilities are virtually endless. On the next slide, we will discuss the potential future of composites and how they can be applied to meet the ever-growing needs of the market.
Now, Jeff, before you move on, could you provide some more specific examples of how polygon composites have been a solution?
Yeah, that's no problem. One of the most common examples would be that many of the businesses we work with are designing composites into their instruments in order to better ensure the insulation of the device and provide a safer patient experience. Also, multiple companies have capitalized on mechanical properties of these composites to reduce impingement in actuating devices. An even more specific example would be for a device that was used to harvest veins. The multi-lumen capability of composites was used to consolidate the various tools all into one device. This took away the need to use other components and reduce the number of steps that were in the procedure, thereby shortening the operation time and improving the patient's recovery time.
Okay, let's go ahead now and move on to discussing the future of composites.
All right. Composites is a new and exciting and ever-changing industry, and as technology develops, new capabilities are regularly realized. For instance, as surgeries require ever smaller incisions, providing tubing with smaller diameters is a consistent challenge to manufacturers. Contiguous fiber composites are currently capable of being produced at small diameters while still supplying a rigid yet sound structure. As smaller and smaller fiber sizes are developed, and other sizes of composites will be able to be reduced even further. This makes using composites for applications such as guide wires a real possibility. Another feature of this type of process is the unique ability for wires and other sensing systems to be continuously embedded in the walls of composites. This potential could also be used in a variety of different ways, from force or position sensing to insulated power transmission, which opens up new avenues for device makers. Composites also have the potential to be produced with unique ID and OD shapes. This can help in improving the stiffness of a device while still maintaining the required size restriction. The versatility can aid designers looking for unconventional solutions to challenges such as cable placement and space restraints. As previously discussed, composites are used for their lightweight and high strength capabilities, often in place of metallics. And as fiber and resin technologies are developed, this will only enhance these capabilities further.
Thank you, Jeff. Now, in a moment, we're going to go over some of the questions that have come across. But before we do, I just want to mention if anyone has specific applications, current or new projects to discuss, or wants to learn more about composites, please feel free to reach out to Sam Hart at the email address on this page. Polygon is focused on partnering with customers to provide solutions that meet applications requirements with the help of our cross-functional engineering team with experience in mechanical design, product design, and composite materials engineering. We have exclusive machinery for prototyping that's separate from our production lines. This allows for efficient turnaround of customized product. It's our goal to be able to react quickly and provide the best solution for your needs. So at this time, we're going to go ahead and transition to question and answer session. Okay. So first question, can you go into a little more detail about how continuous fiber composites are produced?
Yeah, that's no problem. There are a variety of different ways that you can produce a continuous fiber composite. For these types of application, we have seen the best route would be using a process called pultrusion, which takes continuous fiber strands and pulls them through a resin bath and a heated die to fully cure the part. This then yields itself to creating probably the most mechanically sound product for this type of application.
Okay. Next question. You mentioned in the presentation that composites are lightweight but also high strength. What is the weight savings compared to stainless steel?
They can vary depending on the composites and the fiber that are used. Typically, we'll see that composites are around 25% the weight of steel.
Is thin-walled tubing possible with composites?
It is, depending on your application, what type of forces will be applied. There are a variety of options that we can approach and supply the need depending on the tubing you're looking for. Most thin wall that we would just find that as would be down to about a 10,000th wall or 0.25 millimeter.
What other fibers and resins are used with composites?
A variety. I mean, the most common ones I'm sure people have heard of is carbon fiber, fiberglasses we use here for medical devices, Kevlar, basalt is another one, and a variety of other custom fibers from different manufacturers. And then resins themselves, I think we use primarily vinyl ester resins. Epoxies are very common as well. And in some cases, you can also use thermoplastic resins as well.
So would carbon fiber be a good option for electrosurgical devices?
Carbon fiber works very well mechanically. It's a very rigid tube, has great properties. Depending on the surgical application, if it's anything involving electricity, carbon fiber is conductive by nature, so that would require additional insulation added to it, which can just add more cost layers. So that's why typically for us, we tend to stick to fiberglass, because those tend to meet the needs of the device while still providing the insulated layer that's needed.
Could you tell about a tube with variable flexibility along the length?
Since it is a continuous process, the properties of the tube will maintain throughout the entire length. We won't be able to vary wall thicknesses as it's being produced. It'll be one consistent wall thickness going down the length of the tube.
Okay. How easy is it to attach components to composites?
I think Sam kind of tied in this earlier. Most composites, depending on what fiber and resin matrix you use, are fairly machinable. Some of them are a little more complicated than others. But for the most part, composites are very machinable, and you can provide a number of mechanical attachment methods, whether We're talking counterbores, pins, grooves, anything of that nature. Adhesives also work very well with most composites, depending on the type of application and the type of sterilization you may be using, will drive what attachment method we might suggest.
We've also found that attachment methods using bonding can withstand quite a few autoclave cycles. We found that the mechanical bond seems to hold up very well in those situations.
Yep.
Which is good for multi-use devices.
Correct.
How does the strength of composites compare to stainless steel?
Depending on the fiber and resin used to produce the composite, the mechanical properties can vary some. We found that using fiberglass with thermoset resins have shown to provide ample amount of strength to meet the device requirements.
Okay. Can you provide any examples of Polygon products that have been used in medical products different than minimally invasive surgery?
Sam, this seems like a question for you. Do you want to go ahead and take this?
Sure. Polygon's been working with minimally invasive surgery devices since really they came into mass use in the early 90s. But even before then, Polygon's been manufacturing cylinders, cylinder tubing, and finished cylinders for devices like ventilators, as well as other actuation devices. As mentioned earlier, orthopedic fixation. Essentially, if you make a composite rod, it does not have to be a tube. You can have some solutions in that industry. There have been other applications such as bearings can be used since they don't require greasing, but that's more on our industrial side. But there are many different applications, not just on electrosurgical devices, where composites can be used, and Polygon has used in the past.
Yep, answered that perfectly.
Okay. Can you provide further insight into how Polygon started making products in the medical industry?
Yeah, sure. I touched on that a little bit ago, but essentially we worked with a global medical device manufacturer looking for some material for a laparoscopic device. Really didn't have something on the market. A molded plastic wasn't performing or couldn't perform to the levels needed. So Polygon was able to adapt and change some processes to provide what really is the continuous fiber process now, and was able to provide a rigid tube that met the needs of the device. And since then, continue to do that.
Any other questions out there? I'll give maybe another minute or two, and we'll keep checking this group chat here. Feel free to send them to Polygon questions. Okay. What are the possible secondary processes to create localized flexibility different from section of the tube?
Depending on what you're looking for, we might suggest either bonding or mechanically attaching a more flexible section of, maybe it's a silicone tubing or something of that nature to allow for that joint. That'd be the route I'd say we would think of in that nature. The composites itself will maintain the same properties down the length.
Okay. We'll give it another minute here and see if anything else comes through. Okay. Could you talk a little more about the raw material in use? Are there any special requirements?
The raw material itself, for Polygon, like Sam mentioned, we use predominantly fiberglass and vinyl ester resins. Those themselves, the fiberglass is naturally inert, and then once the resin is cured during the process, that is inert as well.
We find that it can work in all in many different surgical applications. It is also able to be sterilized, as mentioned. Autoclave cycles don't cause it to be to have any issues. So temperature requirements tend to be fairly good.
I'm not sure if we've answered that question fully, but
Yeah, if there's a more specific direction as far as special requirements, we'd be glad to answer that.
Yeah.
Okay, we'll give it just another minute here and see if anything else pops up. Okay, it's looking like that's all the questions for today. Thank you, Sam and Jeff. This wraps up today's seminar. Just a reminder, we're going to be sending a recording to anybody interested. We want to thank everybody who attended. We know how valuable your time is, so thank you from our team. And we look forward to working with you in the future.